Hey everybody, my name is Omar Beta. Welcome to my presentation, GitDorker. I'm in your GitHub dorking all your secrets. This tool was created by me and heavily inspired and based upon a tool by Gwenda Lecoqwick, which I hope I'm pronouncing that right, but he is a French tool developer that created a great repository full of GitHub search tools called GitHub-search, and he served as a great basis for creating GitDorker and inspiration for going further into this research for me. Very briefly, who am I? I am a red team consultant at Cylance, also now known as BlackBerry. I am a part-time bug bounty hunter and occasional tool developer. Here we have a synopsis of what we'll be covering. So we'll go over an overview and analysis of common approaches, an introduction to GitDorker as well as a demo, common recon mistakes that people make, barriers to identifying exposures on GitHub, and finally we'll conclude with why GitHub is still vulnerable, and then a Q&A. GitHub Recon Crash Course. There are three common methods of secret identification in GitHub. So we have entropy checks, regex expression checks, and then manual dorking. In entropy checking, we have something similar to a secret, or let's say an API key, which is assumed to be random. So we would use an entropy formula to identify whether or not that string of random characters is actually random itself. If it is random, then we will consider it a potentially valid secret. Now, a quick evaluation of entropy checking itself. While this has a large scope and it's relatively quick to do, it can result, as you can tell, probably a large degree of false positives because many other things could be random, such as endpoints or non-sensitive strings. It's limited to random checking, and it requires a download of data from GitHub itself, as you can't directly perform these checks using the search API. Next, we have regex checking. So say in this approach that we have a secret or an API key or something of the sort that has a defined pattern. For example, we have a Google Maps API key, which always starts with AIZA. We can create a regex check that searches for that defined fixed string followed by a combination of patterns using regex. And we can very easily identify with high accuracy that this secret like this would be valid. While this approach creates a low degree of false positives, is relatively quick, and can give us a very high accuracy of checks on a target or a secret. It provides us with a very narrow scope, as the scope is limited to the regex checks that you provide. It's dependent on fixed patterns for secrets, and it also requires a download or extraction of data from GitHub, as you cannot perform regex checks on GitHub itself. Moving on to manual dorking. So in this approach, we would use a keyword. For example, in this case, let's just say a generic company.com followed by a dork. A dork could be anything, a keyword that identifies sensitive information such as API key, password, connection string, and so on and so forth. In this case, we'll be using the dork API key. In manual dorking, you would combine these two to create a full GitHub dork. In this case, we'll say company.com API key. And then you can search on GitHub manually to identify sources of sensitive information exposure, which you can then validate after identifying. So in a quick evaluation of manual dorking, while it is the most accurate, it provides the widest range. It is driven by human insight and allows direct access via the API or GUI of GitHub. It is still the most time-consuming, and it requires the most expertise, as you still have to manually identify what is valid, what is a secret, what could lead to being a secret, and so on and so forth. Now, a quick overview of automated tool limitations. So kind of like we mentioned before, memory and data consumption due to cloning of repositories. High signal regex checks are often limited to the signatures that are created. So this could be limited to a defined amount, such as displayed on the slide itself. There are certain rules that are being employed in the code of this tool, where regex checks are employed for roughly 20 or so different secrets, no more, as that was the limit as to what could be defined via regex for common secrets known for that tool or employed for that tool for certain regex checks. And then entropy checks, like we explained before, can produce a high number of false positives. Moving forward, introducing GitDorker. GitDorker is a tool that leverages dorking on a wider scale. So the goal of GitDorker ultimately is to leverage human-driven automation to perform dorking on GitHub at scale and to map out potential areas of sensitive information exposure rather than using automation to extract sensitive information exposure, which often has various limitations like we covered. How does GitDorker work? So GitDorker employs the GitHub Search API. You provide GitDorker a query, in this case we'll say tesla.com, and then a file of dorks. So in this case, we'll be using these 5 different dorks for sensitive information. A key limitation with GitHub is that the Search API rate limits you to 30 requests a minute. So what GitDorker does is it allows you to specify a list of tokens in which it will perform a round robin for those tokens to bypass rate limits, and we'll cover this a bit more inside the demo itself. And then using these tokens, you access the GitHub API and perform a search or a code search using this various dorks that you specified against a query, as you can see on the right. So this process has become automated. You no longer have to perform it manually. GitDorker Demo. In this demo, we'll be covering GitDorker, its main use cases, and the additional functionality that I've added to GitDorker as of late to better help bug bounty hunters or penetration testers identify GitHub Recon exposures for their respective targets. And to begin, I wanted to quickly just show the help command to give a brief overview of what can be accomplished using GitDorker. So as you can see, here are the arguments that are shown for GitDorker. Now the most common and most used arguments are up at top. So you see that you can specify a query or multiple queries, a user or multiple users using the file function, an organization. We'll talk a bit more about this command later. It's not really necessary because we can use the user function or the user switch to specify an organization as well. A token or a token file, which are necessary if you want to perform searches using the GitHub API. The -d switch for dorks, and some additional functionality that I've added recently to better filter and to provide better and stronger results or to ease the process of dorking itself. And before we begin, I wanted to quickly show the different dork files I'll be using for this demo. So the first dork file I'll be using is these demo dorks, which is a relatively small file, about 11 dorks or so. And the next file I'll be using is this demo dorks medium, which is a dork file of roughly 48 or so different dorks that I'll be using in this demo. And now for the main use cases. So I'll go ahead and clear this. And I wanted to show you the command for the first main use case I'll be conducting, which is performing a query against a dork list. So in this command, I have the -q switch, which is specifying my query, which in this case is teslamotors.com. There's no specific reason I'm targeting Tesla. It's a relatively safe target, so I don't have any concerns about identifying anything. And this field for the query does not have to be a domain. It can be anything you want, but in this approach, hunting or using a subdomain or a domain of a target is typically fruitful in identifying exposures. And then I'm specifying a dorks file, which in this case is the medium dorks, which contains that list of 48 different dorks for sensitive information exposure, things like API key, connection string, password, and so on and so forth. And then I'm specifying a tokens file, which in this file contains my personal access tokens that are separated by new lines. In this, I've only included 2 for the sake of the demo. And then the -o switch, which allows me to output the results to a CSV file. And we will go ahead and run this. And as you can see, it's currently saying dorking in progress, and it'll give you a live output as to how many dorks are being conducted out of the dorks that have been specified. The stats functionality will demonstrate or show you the different stats of the query that you ran or the functions that you ran. So you can see that you're running one query. There are 48 URLs that have been generated, or 48 unique dork searches that have been generated. 2 tokens are being used. I'm running 1 thread. I would recommend starting off with 1 thread. GitHub has been relatively staunch with their rate limits. It's very easy to get rate limited if you use a lot of threads. And then the current limit of requests that are allowed, GitHub has a search limit of 30 requests per minute. I've set the tool to default at 29 requests a minute, just in case there's some need for leeway between that one request triggering that rate limit. And we'll go into a bit more depth in how to bypass that rate limit later on in the demo. And as you can see, this sleep that's been conducted, the tool will sleep every 29 requests as it's been specified in order to prevent those rate limits. And once the tool has been finished, or the query or the function that you specified has been finished, you will get this output. Now, within this output, you will see that you can see the results. Success is highlighted by a plus sign. Neutral or no results returned is highlighted by a pound or hashtag. And failure, or something such as a rate limit, which in this case we haven't had any, will be shown as a minus or negative sign. And so what we're able to do now is we have this whole map of different dorks that have been completed for our query, teslamotors.com. And so we're able to go into here and say, if we find something interesting, we want to see what is the exposure on GitHub for this dork /rc password on teslamotors.com. So I can go ahead and click that. And it will take me to GitHub, if I'm already authenticated into GitHub. And I can start manually digging through the dork with the keyword that I've specified. So as you can see, all that's really happened is that query teslamotors.com has been added into the search bar, and this dork has been appended onto that query. And so now I can go through. If I see anything interesting, I can click around and start manually digging. But what this tool does is that it enables you to perform this dorking on a wide scale. So with GitDorker, rather than manually entering API secret, API docs, etc., you're able to go through each of these unique dorks, identify what comes back as live or what has actual results, and start digging with this attack map that you're given and specified queries in order to perform more succinct and more detailed GitHub Recon. Now, what this tool also provides, I've specified the -O switch. So I've been given a CSV that's been outputted. And what I like to do is I like to drop this into Excel. And it's much easier for me to manipulate the data, identify interesting URLs by filtering. And I'll go ahead and demonstrate that real quick. So in this Excel file, I have the outputs or the CSV from the dork that we just conducted. And what I like to do is I can take the number of results. I can sort out, if need be, any of the zeros. But I like to sort things by smallest to largest. And it gives me a stronger idea of where to start. I like to start off with the dorks that provide these smallest number of results. Typically, something like config or auth can produce a lot of false positives. So starting off with results that have the lowest number often can increase your chances of identifying sensitive information exposure earlier on in the assessment, or if you're performing a bug bounty test or bug bounty assessment on a certain target. Now, one of the key limitations to performing GitHub Recon, as shown prior, is the sleep that occurs inside the tool, or the rate limits that GitHub puts on its API users. And so, as mentioned, it's limited to 30 requests per minute. So what I've done is I've created a round robin function inside of GitDorker that will rotate across the list of tokens, or the file of tokens that you specify. And using the -LB switch, it will increase the rate limit by 30 requests for each unique token that you use. And unique in this sense is relative to the account. So you cannot have different tokens for a single GitHub account. You must have unique tokens for unique GitHub accounts. So if I have a GitHub account that's been signed up or created with the email omar.beta@gmail.com, I would need to create a separate account with a different email, and both of those accounts will have unique personal access tokens that I can then use into the tokens file to bypass the rate limits. If I were to use multiple access tokens from just omar.beta@gmail.com, the technique will not work because those tokens are still correlated to the same user and therefore will not be considered unique. So to demonstrate this, I'm going to go ahead and perform a query on or using the query file, which will now specify multiple queries. In this case, the queries that I'll be using are the following. So you see teslamotors.com, apple.com, verizon.com, and then I also have the demo dorks, which as shown before contain 11 unique dorks. So we'll be performing a search with 33 total dorks, which is above the current rate limit for GitHub of 30 requests a minute. So in order to bypass this, I've created a function, as mentioned before, and the round robin function and the increase of rate limit requests, which we can specify by specifying the TAC LB switch, standing for limit bypass, and the QF is specifying the query file, the -d is specifying the demo dorks. And now I'm able to run this, and you can see that now it says that there are 59 requests per minute allowed. And again, I've reduced it by one request to give some leeway in case of rate limiting. And it's showing that 2 tokens are being used. We're running on one thread. But now once this dorking in progress meter hits 30, we won't get a sleep function. Rather, the dorking will continue expanding your rate limits. And now we've just concluded. As you can see, the format for multiple queries is a bit different. You'll see each of the queries provided and then spaced out. So you can see here's Tesla. If you want to identify the different dorks that are on teslamotors.com, here are the different dorks identified on apple.com, and so on and so forth for Verizon. Now, as you can see, this is something that would be very beneficial if you're performing wide scope recon for someone such as a bug bounty hunter, or if you're a pen tester and you want to perform queries on multiple subdomains for certain dorks. This is something that can help you cast a wide net and identify in a succinct and insight-driven manner as to where potential information exposure would lie, and create a more automated and quicker approach to manual dorking. Moving on, I wanted to demonstrate the pattern filter switch, which is one of the more recent changes or additions that I've improved onto GitDorker with, and that is specified using the -pf switch. So -pf stands for pattern filter. All the pattern filter does is that it uses GitHub advanced search functionality to negate or to perform a not on certain keywords such as example, test, patterns such as 1, 2, 3, 4, A, B, C, D, X, 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 X. And this is conducted in order to remove certain strings that might be identified in your searches as being false positives. So things that could be test credentials or example credentials would not show up, or there's a much less likelier chance of those instances to show up when you perform your search. And so I'll go ahead and run this so you can see it live. And I'm using the demo dorks file, which has 11 unique dorks. And you can see now that there has been a reduction in some of these requests for Tesla. So if we go up a bit, let's go ahead and see what it was for the secret. So here we see there is 1780 results for secret. Below, using the pattern filter, we have 525. and I'll go ahead and show you what this looks like. So you can see now onto this query, this tesla.com secret, we now have dash fake. Dash is the syntax used to negate or to not search on a certain keyword. So we're removing anything that has a keyword of dash fake, dash example, dash test, and so on and so forth to remove false positives. Next, I wanted to show two other switches for additional functionality that I've added recently onto GitDorker. And we'll use these in addition to the limit bypass, which I've been using, and all these additional functionality switches can be used together. They don't have to be unique. Those are the positive result switch, which will eliminate anything that is not positive coming out into your output, and then the recently indexed switch. Currently, the tool will perform a search sorted by best match. However, if you'd like to change that to recently indexed, so you can identify information exposures, for example, maybe if a target is constantly updating code and you want to be the first one or be as quick as you can to see what's there, what's been indexed, you can switch it to recently indexed. And to perform these switches, the command will be as following. So now I've added -p, which is for only showing positive results, and then -ri, standing for recently indexed. And I'm using all these switches at once. So I have -lb for limit bypass, -pattern filter as well. And I'm going to go ahead and run this command. And as you can see, the dorking has been completed. No longer am I showing any results that aren't a part or are showing 0 results. So those pounds have been removed. And just to show you that now this is being filtered by recently indexed, you can see that now the last indexed will start from the most recent date. So we have 6 days ago, 7 days ago, and so on and so forth. And this will continue to help you better enumerate your potential attack surface for GitHub Recon. Now we'll be covering another main use case, which is to use users or an organization to search on GitHub using a dorks file. So one thing I like to do if I'm trying to identify a user for a company or a target is to simply search on GitHub manually, or you can use tools online that scrape for GitHub users, specifying a query. I will add this function into GitDorker at some point, but currently it is not implemented. So if I want to look for users of Tesla or engineers or developers that are have Tesla in their bio, I'll go to the users tab and I'm going to try to identify somebody that is a engineer or something of the sort. So we have this individual, Alex, who is a software engineer at Tesla. And so what I can do now is to dork on that user to see if that user has potentially sensitive information regarding Tesla on their profile or repositories. And to do that, I will be specifying the following command. So instead of -q, I now specify -u and the name of the user followed by the dorks file, tokens file, and then I'm specifying limit bypass because I'm using multiple tokens. And now I'm able to look into the user. I have a list of dorks that are correlated to that user regarding any public repositories that they have. I'm dorking on this user specifically. I've attempted before to see, and I've checked. There's nothing sensitive on this user. But however, I'd still like to show what the output would look like. So you have user, name of the user, extension, and then you are able to see the different results that the user has inside of their repos. And this, I'm looking for all files with the extension sh. We're also able to dork on multiple users. So I will be using um, additional users that I've found just through specifying Tesla and the user search function of GitHub, as well as the org Tesla Motors. So you can do a quick Google search. If you type in Tesla GitHub organization, you'll be able to find Tesla Motors being their GitHub organization name. The reason you can use the user function and not the org function is because they're one and the same. So it doesn't matter if you use -u or -org. At some point, I'm going to remove the -org function because there's no need if the -u or -uf function already fulfills that need. But I'll go ahead and perform a search using multiple users, and the way I will do that is through this command. So I'm using the -uf for user file, and I'm specifying a user file called using user file, and I will go ahead and run this. And so because there's 3 users and 11 dorks per user, we have 33 different dorks being conducted. And now I have an attack map of the users that I've specified, the org Tesla Motors, as to where to look. And this is something that's very useful if you're hunting on multiple users. Say if you identify on a pen test or if you're doing a bug bounty assessment, a list of users from LinkedIn that are also on GitHub, say developers, engineers, QA folks that have GitHub accounts. Dorking on those users typically is a very fruitful approach because oftentimes single owner repositories do have or are more likely to have exposures or internal information more so than organization accounts, because often those users don't have as many controls or limitations in place to committing code. The last thing I wanted to show is just a bit of a custom query. So there's also a function that you can use called -k, which specifies a keyword. I like to use this to identify or to validate if a user is interesting. So the following command, python3 GitDorker.py -uf user file. So it's that user file that we conducted a search on before. And I'm specifying the keyword -k Tesla. So it's going to append this K or this keyword to each of the users in performing a dork. And what this will now tell me is if that user's repository even contains the word Tesla. So if that user doesn't, then I know for a relatively strong certainty that that user probably isn't interesting to me because they're most likely not carrying any sensitive information relevant to the company that they work for or the company that they previously worked for. This isn't always the case. I mean, there's always edge cases where somebody does have something, but I've found searching on a domain or the company name across a wide list of users helps validate interesting users to search on and saves you time in dorking. So I'll go ahead and run this. And we can see that the users provided, they don't really contain the keyword Tesla. So in my approach, I would scrap these users typically and go for different users. However, Tesla Motors, for obvious reasons, does contain the word Tesla in their public repositories and is still a target that would be of interest. Now, this covers the majority of the main functionality for GitDorker, but I do want to highlight that ultimately GitDorker is a very simple tool in nature. However, it's fueled by human-driven automation and insight. So the dorks that you give it, the filtering that you do, and where you choose to search ultimately is all dependent on the insight that you provide for a target. So understanding your target, what's behind your target is extremely important. GitDorker is a tool that will enable you where to search, but it will not excavate or give you the secret itself, such as something that like a GitRob or a TruffleHog will do, which typically do contain a large degree of false positives, or they don't cast a wide enough net to identify things such as employee created passwords and only search on computer generated secrets. So automation is important. However, I believe GitDorker utilizes automation in a human-driven and a insightful approach in order to generate an attack map of where to look. And ultimately, I feel that this is the better way to dork and to identify and to have a full breadth of depth into your GitHub Recon for your target. I hope that demo was beneficial and enabled you to better understand how GitDorker works as a tool and the benefits of GitDorker. But I wanted to also cover common dorking mistakes that are made by hunters or penetration testers. The first mistake being that oftentimes people try to search what everyone else is searching, or searching on keys or secrets that are being actively scanned for. So for example, service providers currently that are partnered with GitHub use GitHub to prevent leaks in repositories using a high accuracy regex approach. So GitHub is able to actively scan for the leaks of the following credentials. And this list is available online on GitHub as well. But some common things that people dork for or look for are things that are being actively scanned for, which can reduce your chances of finding something such as a Slack API token, or GitHub private key, GitHub token, an AWS access key ID, or secret access key, and so on and so forth. While it's not impossible to find these, it's much more difficult due to the active scanning prior to the commit or prior to the indexing of these unique secrets by GitHub. Another common mistake is not customizing your dorks to the target. Dorks are often generic. However, your target is unique, and you should be searching on specifics. So for example, subdomains or unique subdomains that might elicit internal exposure, endpoints that are unique that you could search on using your dorks, variable patterns. So if you're getting into your GitHub environment of a client or a target, understanding how they're naming their variables, something such as API key might not be just API key. They could have something that's unique, such as new underscore API key 3, or however they're naming or whatever their conventions are. You can dork on that to create better success. Custom strings that you identify on your client or target. Technologies, understanding and analyzing documentation for the technologies that your target is using to create dorks. And then finally, user patterns. So for example, oftentimes a target or a GitHub environment might have users that are creating certain accounts using a set defined pattern. So for example, a defined pattern could be Omar underscore company name. And that could be an easy way for you to identify what users to dork for. That could be interesting. Finally, or thirdly, not using advanced search parameters. So you can dork using customized dorks with extensions, file names, like I mentioned before, users. You can exclude certain keywords such as test or example to filter for secrets. You can dork specifically on a language, and this is something that you can customize further in creating your dorks, which would be very helpful in identifying specifics when performing GitHub Recon. And then lastly, not digging deep enough. Automation is great, but it can't replace human insight. For example, if there is an image on GitHub that contains secrets, automation is not going to be able to pull that out oftentimes. Searching and identifying what users are vulnerable, what endpoints are vulnerable, what's considered an internal disclosure, or human-generated secrets are difficult to uncover with automation. And ultimately, the ability to evaluate company or a target's context can be pivotal in finding secrets on GitHub, not limited to computer-generated secrets. So very quickly, some barriers to finding secret exposures. So like I mentioned before, regex patterns are being used to actively scan against secrets, and developers are now actively being trained to prevent commits. But GitHub also has its own search limitations. So for example, certain characters are ignored. You can only search or display certain files through code search that are smaller than a certain amount. Fewer than 500,000 files are searchable on repositories with fewer than 500,000 files that are searchable. And then finally, like I mentioned before, there are API rate limits being conducted by GitHub. Why GitHub is still vulnerable? So in 2019, there was a case study done by a team of researchers at North Carolina State University where they analyzed and queried about 2+ billion GitHub files. What they discovered was that there were roughly 4 million plus code files that were identified using dorks or certain strings to identify them from. And they were able to identify roughly 200,000 plus unique valid secrets using an approach combined with regex and entropy searches. What I want to do is go over some of the key findings that they found from this approach and from their study. So they identified that a majority, 93.5% of all secrets discovered, belong to single owner accounts rather than multi-owner repos. Multi-owner repos being something that we could consider an organizational account or something that's shared between multiple users. Another key finding is the fact that the short and long-term monitoring of secrets is a bit contradictory to what we expected. So secrets are removed in the first few hours of being committed. However, despite being discovered, the majority still remain. In fact, roughly 84% of secrets remain after 16 days of detection, and secrets still exist on GitHub for roughly a day after a commit, tend to stay on GitHub indefinitely. So secrets are still out there. It's just a matter of identifying where they are located. A third key finding is that roughly or over 80% of all secrets discovered were found to be within cryptographic or source code files. In fact, you can see a breakdown here on this bar graph on this slide. Cryptographic files being things that might host things such as private keys, code files being things such as JavaScript files, Python, Go, so on and so forth. But this indicates a better understanding of where we should be searching rather than text or potentially JSON files if we want to identify information exposure at a quicker rate. From this study, we can gather a few key takeaways. So targeted user hunting to identify sensitive information exposure is often far more likely to be successful. Secondly, the majority of secrets not removed within 24 hours, they tend to persist over long periods of time. Oftentimes, when something's committed, developers will check a commit to commit, but not often is it checked for the whole history of commits, where an attacker or hunter could go in and find through that history a secret that's been exposed and not reviewed after missing on the first commit review. Lastly, secrets are more likely to be found in source code, cryptographic or similar files used by developers, engineers, QA folks, so on and so forth. Now, I also wanted to highlight some areas of improvement that the researchers also touched upon, was that this study focused on a very limited scope of secrets. In this case, common API keys and common regex formats to identify them. All secrets discovered were computer generated, so this does not take into account secrets that are either not encompassed by the regex checks or by secrets that are human generated, such as a password or something of the sort. And then finally, kind of to touch upon the previous point, is that automation overlooks many secrets. Because of the limited scope of regex checking, while very accurate, it can overlook many secrets that are not within that scope of regex searches provided. I hope that this provided a better understanding of GitHub Recon, and I hope that it provided a better understanding of how GitDorker could be leveraged to perform insightful GitHub Recon at scale. If you'd like to access GitDorker, the code is available on my GitHub at obeta12. You can contact me if you have any questions or suggestions or feedback for the tool at Twitter or LinkedIn or GitHub. Please feel free to reach out for anything regarding GitDorker or any needs. References that I've included as well are on this page. If you'd like me to send anything over, please again feel free to contact me at any time. And that concludes my presentation. If anybody has any questions, I'll be taking them now.